architecture, books, and conferences. Why am I having these challenges with architecture and putting it in place? Is it just me, or is there something fundamentally wrong? So I'm going to spend a little bit of time talking about that. I'll see this first. So first, thank you. Thanks for coming on. Monday night. It's great weather. And I noticed as I'm walking up here, there's lots of people I think outside enjoying beers and drinks. As the papers say, it's going to be cold the rest of the week. So I will try my best to get through this as fast as possible so we can get outside. And Tangosol, we're going to sponsor a few drinks. I'm being told to put my card behind the bar. I have to stay until the last person's left. So it's Monday though. It's Monday. I have to work tomorrow. So thanks a lot for coming on. So I was going to talk a little bit about saving holidays and not too much about saving holidays. Basically, when I'm on holiday, I really don't like to be interrupted. And systems failure is the usual reason why I'm being interrupted, not because there's some algorithm that needs to be worked out. So I'm going to talk a little bit about production issues and how it relates to SLA, grids, and in particular coherence. I'm going to give you a fairly hardcore demonstration of coherence, which I hope you'll enjoy and take something out. Okay. So, agenda for today. I'm going to be fairly use case driven. I've just got one use case, and that's going to be a trading system. So I'm going to give you an overview of the trading system, show you lots of diagrams and models. Then I'm going to talk about what an SOA, sort of trading system, SOA sort of design what a trading system looks like, and what it typically feel like. I'm not going to spend too much talking about SOA because I think everyone understands it. And then I'm going to talk about data grids and the goal of what they're for. Through this, I'm going to give you I'm going to blue sky some features. Then I'm going to do a demo. And in this demo, I've got real code. I'm going to run it in front of you. It could break. It's always weird with doing a live demo. It's worked heaps of times in rehearsal. And there's this new term, or Gartner's coined this term, extreme transaction processing. And what does that mean? It doesn't necessarily mean financial systems, but it means extreme manipulation of data at really high rates, be able to scale it out reliably. And typically this means without a database. But there's nothing against databases. Databases have a purpose, but the types of scalability I'm talking about is being able to add a new piece of hardware to running the system as it's working, as there are users hitting it, and just have it share load. Without having to go to a console, without having to manage anything, just start another copy of your application and keep going. And just keep doing that until you run out of network. And that's the sort of system I'm going to show you today. And I'm going to show you the code. It's very, very easy to build one of these things. I think it took me about 3 hours from start to finish. Mainly because I was stuffing around with a few things, but as you understand trading system models, I work on about 7 classes. It takes almost no time. The hardest part was working out how to match engines. Then I'll talk a little bit about data grids versus clusters and give you a sort of high-level comparison about where these things fit and how do they compare with clusters of grid technology and data grid technology. What's the difference between them? And then I'll make some random conclusions at the end, which I'll just make up as I go. Okay. So, trading system, as I said. So, what do one of these look like? Quick question. Who's used coherence? 2 people. That's great. Who built the trading system before? We're all the experts. Who works on a trading system? Okay. Who buys and sells shares? Does anyone like doing personal trading? Or have ever done personal trading? Has anyone used Betfair before? Done some PHP gambling? Alright. I'll give you a brief overview of trading systems. So, looks like this. Trader, could be you. has a desire to place, to buy something or sell something. For example, using eBay. eBay's a customer. Place an order, and there's usually what's called an exposure management system. It's part of risk management. It says, basically, do you have enough cash to buy what you're saying you're going to buy? Are you going to go over your limit? Sort of things. It's pretty simple. But in order to work out exposure, you have to know how much cash you've got, positions, stuff you already own, trades that have already been placed in the market will get settled. That is, you've got an agreement, there's a handshake that you're going to buy or sell something, but you haven't actually exchanged money or an asset yet. All of the orders that you have in the market, so you say, I want to buy Oracle, that's an order. I haven't bought anything yet, but it's in the market and I'm waiting for it to fill. And usually it's some sort of structure containing all of my orders, or all of the orders together. So, typical process, dramatically simplified, is trader decides they're going to place an order, the exposure is checked, the orders go into some huge vat of orders, then they go into some engine which tries to match the orders up. It's the marketplace, so you've got people who are buying, people who are selling. It's a massive eBay, if you like. Pretty straightforward. And the engine itself looks at all the open orders and tries to match them up. How do the stock markets make money? The more they match, because they take a clip or they charge a fee, the more they match, the more fees they generate, the more money the markets make. And out of that, when there's a match, when there's an agreement between trades, the price is sort of published. So when you look at the Financial Times or you look at Betfair's moving markets page, they're the prices that are on offer or prices that are recently traded. So when you match the trade, agreement to buy or sell something, you go to a big market called the trades group, trades. And at the end of the day, we go through this process called settlement. And that's sort of like at the end of the night when you walk around the trades and you just settle up. You have to pay what you've spent, or you get paid what you've sold. And of course that just goes around to the loop. So the bit that we're going to build, well, sort of build, we're going to talk about is this bit here. And we're going to look at doing all of this without a database. But I want to make it resilient because I can't lose trades. So I'm going to trade as fast as I can. So I'm really going to trade, say, execute a trade resiliently in like half a millisecond. And hopefully it will work. Okay? So what's this really got to do with web systems? Well, it's somewhere like Betfair, and somewhere, Betfair is a really good example. Their web front-end system has a huge amount of hits. The number of hits that occur on their front-end website is massive. And managing the state for all of those sessions is very difficult. It's not something you just throw into a database. You can, but you run into all sorts of scalability issues. So one thing that Betfair does, it uses coherence as a product to manage the state of their systems. So this is just one example. Just managing the state of all the orders in the market at once. But it doesn't have to be traders. Another really good example is something like MTV. You think about MTV as a global company, big TV presence, but massive online presence. I don't know, 30 different companies. It's like Nickelodeon. And you think, well, they've got this huge amount of data. Their prices, the equivalent of their prices are clicks on a website. And imagine like when SpongeBob comes on Saturday morning, they're running some advertising campaign and MTV want to find in real time what their campaign looks like globally or across Europe. It's challenging to go to a database and get an instant view of that. So even clicks, a click is a piece of data that has some state attached to it, has semantics that are interesting. And in fact, trading systems are actually quite boring. It's those systems which are far more dynamic because they move quickly. The markets move, the people, the kids move, they click on stuff randomly almost. It's very hard to predict. Markets I find are far more predictable. That's what we're talking about. So we're going to build one of these. So these slides will be available through the usual channel.
That would be on the website, on the blog, so I'll post something.
So I've got there's a whole heap of slides here about terminology which I'll use, and I'm not going to go through all of these. We'll sort of talk about them briefly anyway. The interesting thing about orders is how they're executed or how they're matched in the market. So when you place an order into a market, there are a whole heap of rules. With eBay, it's sort of like classic example with eBay, like you bid on something, which is an order, and the bid lasts until the end of the auction. So the lifetime of the order is quite long. But there are lots of different mechanisms for placing orders. You can say, look, I want to place an order and what's called kill or fill, and the order gets matched straight away or it's killed. Or you might say, I want to place an order and it's going to last for 10 minutes. After that, then it gets killed. So there's a lot of complexity about different types of rules, different types of ways you can match things in the market. What we're going to do is something what I call perfect match scenario. Whereas someone will place a bid, and someone will make the offer, and they'll just match perfectly for the exact same amount. However, the code that I've written will actually code with imperfect matches and sliding scales of prices. So those are familiar with Betfair, it's almost precisely the Betfair trading model. Okay. So a couple of slides on so we talked about a trade or a fill. When two orders match, we say we had a trade. Or often we say that the orders have been filled. And you have what's called a partial fill, so not the entire order has been filled. You say, I want to buy 100 units of Oracle, I want to buy 100 units of Oracle, and someone can only sell me 50. So I've got 50 unmatched, unfilled. An open order is one that hasn't been filled, so in that case my order will still be open. And a closed order is one that either has been killed or completely matched. Okay? We talk about a position the markets when they say, well, how much do I own of Oracle? I own 0, that's my current position. Now, if you're not trading, everyone has a position in every market globally, it just may be 0. So, there's a whole heap of other types of positions we call, there's a theoretical position. It's the position which I know I have, plus some that I may have because I haven't been matched yet. There's my actual positions. And there's a desired position. It's like, I really desire to have more Apple shares and I want so much value. But I don't actually have it yet. Maybe I can place the trade. Okay. Any questions? Cool. So that's the use case. So let's do my service orientation refresher in 3 slides. I think it's 3 slides. The cool thing about the web is this thing called Wikipedia. I don't know if you guys have discovered it yet, but it's very, very cool. If you look up anything, it will tell you pretty much a good definition. But Wikipedia, so I was looking up what would be a good definition of SOA, and the first thing it says is there is none. There is no widely agreed upon definition of SOA. So I'm free to rubbish it if I want to. I'm free to make up whatever I like. But the general consensus is that it's about service orientation. And I've tried to look that up, and then there's a list of characteristics. But what it does say is all of these technologies aren't SOA. It says that they're technologies that implement some of SOA's sort of fundamentals and principles. So, the common sort of misconception is if you use web services, then you must be SOA. That's not quite right. It helps. It's very much close to the principles, but not completely SOA. So what's this concept about service orientation? Well, goal is loosely coupled. That's the #1 thing. And that means no compile time bindings. And one of the other things that's not mentioned we'll talk about is, we talk about coupling between services, but we don't talk about coupling between the software you write and where it's deployed. And in production, that's very important. SOA doesn't mention that anyway. Like, if I'm going to deploy a database, I have to know where it is. Unless you use DNS, ALE, and stuff, I'm tightly coupling my service, or the database or my data service, to this part of it. And that's completely against SOA. There's a whole bunch of other characteristics, and most of them seem to end able or ability. Let's talk about being able to interoperable with low language dependence, dependencies, everything does the contracts, you should be able to compose them together, you should be able to abstract over things, which as soon as you add a layer of abstractions, you're going to cause some performance issues. Autonomy, and you should be able to discover them randomly. So you should be able to walk in a room and say, hey, I need a service because I'm going to do something random, I want to bind to it, I don't know what I'm going to build, but there are some services I can discover. And some of these actual fundamentals mean it's almost impossible to scale out. Because you have to look them up, and as soon as you have to look them up, discover them, you introduce a single point of failure. Because that service discovery has to live somewhere. So if you're away on holidays, and the service that delivers lookup services dies, then everything else is dead. So then you have to do a lot of other things to make it survive. Have a service, or a backup service. Okay, so there's a great model, and if you go to Wikipedia, this is what they call a meta model SOA. But it says it's really this mixture of stuff. And all of this, it has this thing called services in here, which is like there your business service, I think you offer. But everything else is a service as well, so the security service, government service. And it doesn't really say how these things fit together, it just says go from there. So let's think about our trading system here. Let's go back and say, well, what would it look like if it was an SLA? So how would you design a trading system as an SLA? What's the first thing you look for? Well, pick out all the verbs, their services, they're doing things. Just pick all those out, they're your services. Then, well, how do I tie them together? I know, we could use an enterprise service bus because I can get one of those and put it on my CV, it would be very impressive. Or I could use some messaging, but let's say I could use an ESP. And so I could magically transform my previous diagram into one of these. So I said, well, I need an order placement service where I can connect to, and I'll place my order there. And then that, because I don't want to tie anything together, I'm going to have this thing which lets me locate services and route things. So an order goes in and goes, oh, it's a new order. And then the order validation of exposure service goes, oh, I see a new order, I'm going to validate that. So we're completely loosely coupled with it. It says, well, I need to get cash and then what orders. In reality, it needs to know a whole bunch of stuff down here, but I've sort of left that out. It makes it quite complicated. And when it's finished, it goes, hey, this order's valid now. And so we know it's valid for a certain market, so we're going to buy Oracle. So one of the engines here that matches the market says, hey, I'm the Oracle engine, I'll take the Oracle order and now I'm going to look at what open orders I want to see if I can match it. And if I do match it, then I'm going to produce a number of trades. Some trades, I'm going to throw that back in the bus, and then it will then magically pick those bits up and say, well, the settlement system needs to keep track of these because at the end of the day I need to transfer the money between parties and transfer the assets. And obviously there's a price feed that needs to notify all of our clients that we've done some trades and this is the latest offers, etc. So, sort of made it up. It's incomplete. There are lots of bits, but it's very nice though. Let's think about it. We can have a separate team to build, a separate team that looks up the data, so all these orders and trades. We have a modeling team that looks up the modeling and messaging. We have a team that looks up the ESB or the management of that. how it all fits together. So each team, like I've got a database team looking after their stuff. We've got teams that can work in isolation to build this thing and just glue it all together magically. Okay? That's fine. The interesting thing I thought about, well, maybe it was interesting to me, was, isn't this just called human-oriented architectures but done with software? Like, if you think about a company that doesn't have any computers, and now what we do is implement the same thing. I could have, and we're just shuffling paper around. I could have the order placement department, like a department that deals with order valuation. I could have a department which actually does matching. Each of these departments has a manager, or it can have its own registry of other sub-services, so I can compose them all together. I've obviously got security people entering the building, but I can governance and orchestrate all those departments together. So, I don't know, it was just a question, it's a bit of a side topic here. Is this actually necessary? And do you find this in the architecture you see? And to me, I often see this. So instead of databases, we have corporate resources, we have suppliers instead of legacy systems. If we build systems like this, like the human-oriented ones, you have exactly the same challenges. So you know that in order to place an order, I can go and see Joe in the order placement department. But Joe's on holidays. Suddenly I can't place an order. How do I fail over? Joe's not here. I don't know of anyone else. Now I have to go and look someone up to place the order. So we tend, for some reason, to build systems like this. I'm just waiting to get here. But computers aren't like that. Computers don't need to have a role defined to make them feel good. I personally like to have a well-defined role in my job. But if I was a computer, I'd care. Just like, well, 1 minute I can process an order, next minute I could be matching, next minute I could be, working out exposure or doing settlement. I don't need to be put in a big pool that says, you guys do that, you guys do that, you guys do that. So then if some of them fail, I want the other guys to help out. So it's a challenge in SOA. So to build, design flexible and maintainable systems is great. Compose solutions is great. To improve software engineering. Now, what's the difference between engineering and development? Developers don't care about economics. General classification. Economics is about software development lifecycle, the cost of the software development lifecycle. If you just like developing and tinkering and don't care about lifecycle, then if you like writing code, then you're a developer. If you're really concerned about how long it takes to go through and what happens in production, you're probably an engineer. That's my loose definition. One cares about the economics, the other doesn't. So again, I completely ripped off some stuff from Wikipedia. It describes a whole heap of things from reuse, granularity, modularity, componentization. It talks about, we have to have compliance to standards. We've got WSDLs, we've got IDLs, all of this sort of stuff. All of this stuff's there. It talks about, Gini's got a fantastic way of registering service identification. You can do leasing, you've got all these cool things that you can build an SOA with. What it doesn't, none of these are sort of as exhaustive search as I could find. None of them talk about operational production characteristics of any SOA. It's not mentioned in any definition I've seen. It's just, I don't know why. These are the things, reliability, maybe that's just something you tack on. These things aren't mentioned. Security is often mentioned, but funny enough, it's something that's added later. Think about web services when it started, security wasn't part of the initial spec. It was added later. Transactions weren't part of the initial spec. It was added later. All of these other features get added later. But, so you can think, well, if I can add loose, how hard is it to add loose coupling to a system when it's built? Pretty hard. So, how hard is it to also add availability and reliability? There's no magic, I'm just going to add reliability. I'm going to go to my compiler and go, add reliability now, add loose coupling. these things all have to be built in. They have to be part of the consideration when we're thinking about SOA. So, general personal opinion. You have to avoid SOA approaches and technologies that are unknown or untested operational characteristics. Any of these production characteristics I talk about, availability, reliability, all those abilities, if they're not mentioned, that to me raises a flag. So what I'm talking about is an API. It's fun, it will help me write some code, but at the end of the day, this thing has to run. Because that's my job. This has to run in production, I have to deliver some service to an organisation, and that's what I have to do. So, if you don't have these things, you have to destructively test an architecture beyond your expectations. So if I know I have to do 500 trades a second, I know I need to at least try and make it 2,000. I'll just pick something. And that's what engineering is about. You build a bridge. You don't build it, I can fit 4 cars on it, therefore I'll test it for 4 cars. You stack massive numbers of vehicles on it and see where you break it. So there's this, a good friend of mine said, hope is no method. I don't know where he got this from, but the concept that you hope that the architecture is good enough. Well, he was slightly less talking about architecture. He was saying, I hope I don't get some disease while you're engaging in some risky activity. So you're either crossing your fingers or handcuffing yourself to something. So this is what I was talking about before. The SOA stuff, so they're often focused on providing an API first. And then at the end of the day, you end up testing it in production. The developers are. People who build the APIs, they're just like, here's a spec, someone builds it, and then you somehow test it. And as clients, as customers, as developers, you often do this. Okay, that's my rant. Introduction to data grids. Okay, so data grids, let's be honest, data grid is a marketing term. It truly is. Most vendors in this space, whether it's Java or any other space, that somehow keeps objects in memory, pretty much marketing their stuff these days, their events, as some sort of data grid technology. Because it manages data, and if you get a big collection of computers, we can call it a grid, and therefore it's data. So, fairly cynical view, but that's pretty much what's happening in the market. So, but what does it really mean? Are there any purists? Well, I thought, well, let's imagine some things. So, imagine if we could just get a couple of applications. We've got 2 instances of your application, and they just both work together. They can want 4 instances, or 5 instances, and they can just work together. That's all I want them to do. If one goes away, the others sort of go, yep, I'm going to keep going. It's like a cluster, the ideal cluster. Usually when you talk about clusters, there's some sort of master or some primary, and that's doing all the work, and just in case something happens, you have the same size piece of hardware, which is not doing anything, just sitting there waiting there. I'm ready. Anytime you're going to fail, I'm ready, as you back up. And when your primary fails, then you switch over. No, I'm not talking about that. I'm talking about all of the members of the cluster have the same responsibility. They all work together. If one goes away, then the rest pick up the work. If another one joins, and they go, oh great, more people share the work with. It's almost like I call it like a perfect sporting team, where every member of the team can play every position, and if someone gets sent off, it doesn't matter. You can bring another person on and carry on as if nothing happened. That's what I'm talking about. So they each take responsibility for the group. They share workload, they share recovery. You can bring in new members without having to stop the team. Imagine if you had to bring on a new person who joins your football club, and then during the game that person's never played with the team, the whole team has to stop when that new member comes on, like in the middle of the game. It's just not acceptable. It's the same with software. We shouldn't have to stop the game to let new members join. So you can imagine this land that has no slave time masters, and this means single points of failure. If you have a system which has a master-slave architecture or master worker pattern, then you have single point of failure. You have to do something about it in order to recover. if you have a system which maintains a registry of something, then you also have some sort of single point of failure. And even if you try and back it up, you've still got a single point of failure. We'll talk a little bit about this shortly. Imagine a land without containers. So these days, who uses containers to deploy their systems? Everyone? Right? Imagine a world where there's no containers. It's just Java. It's just not there. You don't have to use facades or AOP or white code injection. They're all cool, but they're cool, but they're hiding something. Right? Well, having specialized JVMs. So, yeah, there's a whole heap of things here. The one that I particularly get, it's frustrating. I don't know about you. If you ever have to handle remote exceptions, what do you do with a remote exception? What does it mean? I've tried to establish a conversation and I've got an exception that says the service is down. Will it retry or has it already retried? So there's lots of things we can imagine. Look, my favourite is being able to share state. To share state, rather, how many ways are there to share application state? Right. You can have the processes running on the same piece of hardware and they can share the memory. Talk to the operating system and say, I want to share the memory between them. You could do that. You could put it in a database and use the database as a place where it shares that. That's the classic one. Or you could maybe have all the applications keep a copy of the same state, in which case it's got a lot of communication and we're going to be sharing stuff around. That's a real hard one, because how do you keep them all in sync? So sharing state, that's my goal, without reconfiguration, and without having to introduce a weird pattern. All I want to do is share stuff. I'm going to put stuff in my program and then another program will just pick it up and use it. That's all I want to do. It's small ask. I want to know if stuff changes, and I just want to use like beans, so I'll add a listener to the swing style. And once I have all this data in memory, I'm going to do stuff with it. I'm going to say, hey, all new trades, all trades for Oracle, hey, it's been a stock split. You should double your position. Sorry, double your position. Okay. And I don't have to be like a master of distributed computing or parallel computing to do that. So that's coherence. Coherence lets you do those things. So let's transparently share state. You can manage application state across just normal Java programs, so the cluster, and we can make it really sexy and add more words to our CV by saying grid, but it's just a cluster. Grid really means a set of managed resources. Usually in a grid is a grid manager which knows all the resources and knows what type they are and lets you schedule work amongst them. We're usually talking about many, 10 plus machines here. Coherence is often, you've seen the server-side camera tools. It started as a caching product. Well, it's actually more than a caching product. Caching just means you're going to expire some data. You have that, we just don't expire data. Now we have some shared memory that we can scale out. So, in the areas that I work in, we're more saying, well, we're not really caching data. We're going to do some transactions. I don't want the data to go away. And, as I said before, it's just data. So, a great piece of data is a session. A client's logged in a session. A great piece of data is which parts of the web page need to be regenerated. It can all be cached. Anything that you have to generate and go to a database for, you can cache it for the database. We're talking about plain Java objects. You have to make them serializable in some way, but they're just plain Java objects. Code doesn't do anything to them special, they're just objects. Or they're .NET objects. And it's nice, you can put in .NET objects and pull them out as Java ones and put them back in Java, even though it's .NET. Put .NET objects in and see events of Java and do the same on the side. And soon we're going to use C. Coherence is a single jar. There's no open source dependencies. Not that open source is bad, but it's a challenge if you've got lots of them. Lots of applications where you think, oh, I just want to use this library and suddenly you pull out this dependency of 20 or 30 different open source projects that you didn't really want. You just want this one. And the challenge with that is you're using that one there and that one there, and they're using different versions of the same dependencies. You've got an integration issue, you just introduced. So coherence, everything's in one jar. It's all Tangosol proprietary. We even had to build our own XML parser because there wasn't a standard one we built. Logging, everything. Built a whole lot. So there's no way you'll get a clash. No external dependencies. You can use it as embedded for managing data or service. And so we're at the JAVAWUG. Okay. Any questions?
What's the job?
How big's the jar?
Not very big.
The DLL is like 200K. That's fine. It's really small. And the coherence one, you get everything. You just get the whole, every feature in one jar. We could split it out in little jars, and so we just ship the whole lot. There are other jars if you want to do some Spring integration, or if you want to drop in and replace your web session management, there are separate jars for doing those sorts of things. Workload management and cluster, they're just add-ons around coherence. Okay. People say, what's coherence about? This is it. It's about one thing. On top of that one thing is all that stuff. One thing is cluster management. That's all it does. It manages multiple JVMs in a cluster reliably. So it means if I start a process up, a JVM process up, and then I start another one up, they'll discover each other, and they'll know, and they'll work together then to manage each other. If you start another one up, the three of them will work together. If you start a fourth one up, four of them will work together. If one decides it's failing for some reason, usually in the training course I spent about an hour talking about different ways JVMs can fail. Most of it's nothing to do with Java. If one fails for some reason, the three work together to determine the health, and then they have a team. That's it. And you think, well, okay, cool, it's a networking thing. But what it means is when you know all the members that are part of a cluster reliably, you can then reliably share data. You have this guarantee that you can put your data anywhere within the cluster that's alive, and it will be there. We can also back up the data to other members of the cluster. And we can do the same for services. So on top of this cluster protocol, which really it's proprietary peer-to-peer, it's a bit like one of those peer-to-peer networks where you go to get a file, download some file for some reason. There are billions of copies of it and they all work together to get the file. It's a bit like that, but it has this consensus protocol to ensure that there's consensus about membership and health. And it does so without any of these things. With none of these things are really coherence. There's no registries of who the members are. You can find out. So there's no one node which says, hey, I'm the registry of all the members. It's not really works like that. There's no single points of failure, so you're free to kill any process you like while it's running. And I'll do that. I'll show you that. So there's none of this separate stuff. It's free of all those. Because we know membership, coherence knows membership, you can do load balance data across it, load balance services. You can reliably execute operations against it, even when there's failure in recovery occurring. Even as you add more resources to the system, it will just continue to scale out while it's running. And the last point here is to ensure reasonable decisions are made. One of the challenges with clustering, so clustering technologies, sort of say like, I would talk Baraka and say, hey, I'm just sending jobs for you to do. Okay? Certainly Baraka's asleep. Right? But I don't know, all I know is that I've not received any messages back from them. So I sort of go, well, what do I do? I haven't received acknowledgement for the last bit of work that I sent. So I'm going to now talk to Steve. So I resend the work to Stephen. Greg wakes up, goes, that's a message. So he starts doing the work, and Stephen starts doing the work together. Immediately, see what's going to happen here? I've got duplicate works going on. If I'm placing orders in the market, I'm in trouble. Because we don't have consensus between us about who's doing what, and who's alive, who's asleep, and who's not. See, without that core technology, it is impossible to scale out reliably managing data. There is no other way of reliably managing data in the cluster. You have to resort to mastering slaves without a technology that lets you understand consensus between the group. There are a million little edge cases, I'm sure, about this. So, coherence does this. Now, is coherence the perfect solution? No. By no means is it the perfect solution. But after enough years in production, we've got it very reliable. I'd say pretty reliable. Could we still find more edge cases around this? Absolutely. So, by no means I'm saying it's the perfect solution, because there is no perfect solution for this. There could be all sorts of issues. I'm sending messages to Barry, and he's actually alive. He's actually awake. It's just that there's some fault on my network card that I think that he's not awake. I can't see. So then I have to there's all these different ways that we can tell health in the cluster. And that's what we've spent all of our R&D on. Pretty much all. Once you've got a reliable cluster, then you can do heaps of stuff. So let's look at how coherence works. So, this is a classic popcorn, we call it popcorn diagrams. We've got 4 pieces of popcorn, A, B, C, and D. And I've got 4 JVMs, which just start at 4 processes here. And I'm using what's called a petition cache. And petition cache is just a name for something some vessel I can put data in. In this mode, I have embedded the data management. So I don't have any, I could have some nodes that just manage data and do that. But I've actually got 4 applications that are identical. Absolutely identical as application. So I can put A, B, C, and D. And what coherence does in a petition topology is it petitions your data and spreads it out across the cluster, across the members. We also have 4 members here. So A is here, and B's over here, and C's here, and D's there. We also have, so we've got primary petition. Now I talked about primaries and backups before. This is slightly different, you'll see why. I've got backups as well. And what I do is I petition the backups away from where the primaries are. That because I want it to be resilient. I don't want to have the backup for A on the same JVM, because if that dies, then I've lost A. So if I want to get A, and in coherence, this interface here is a map interface. Well, there's many extensions of the map interface, but it's just, I just say get any key, and use any key, any key, object, serialize it, whatever you want. And there's many topologies, but they all use exactly the same interface. So you can switch out your topologies based on SLAs or based on performance requirements. You just chop and change them. Want to get A? This petition knows that it's here. I want to get B. When I ask this petition, it says, well, I don't have B. It's over here. Now at this point, you think, well, how does it know that? It must look it up. Well, no, it doesn't. It knows where all the objects are. Based on the key of B, sounds like a music, the key of B, it creates like a hash of it, and that hash based on the number of members and the number of petitions will result where it is. So it never has to look up, doesn't have to chat to any other members and say, hey, you guys, which one it's got to be? Can you tell me? Send me a copy, but I need one. It knows it's there. If it wants D, it's here. If it wants C, it's here. So, worst case, to find any piece of data, to get any piece of data in this topology, 1 network hole, regardless of how big the cluster is. Scalable by design.
So that hash contains the backup decision as well?
Yes. And we'll soon see how this works.
Sorry, I know you probably look forward to about that later, but it's based on the number. You can add extra ones in on the fly.
Yep.
Okay.
Yep.
I'll wait then.
Yep. Okay. So the nice worst case has to get it across the wire, or across a loopback, or across a machine, across the process memory. Best case, it's in process. Okay? Predictable, guaranteed, deterministic access pattern, regardless of the size of the cluster. Now, how about quantity of data? How much data can I put in this? Well, reality is, it's dependent on how many JVMs are. So if I need more data to handle, I add more JVMs. Just start them all up. Okay? I'll auto discover, and we'll show this in a second. I'll auto discover and say, great, more data, great, pile it in, and it will load balance the data for you. Okay. I'm going to go slow through a few of these, and then I've got a whole stack which I'll just rip open. When you download, you can sort of see what's going on. So if I do a put of A, I have to actually back it up. So when you do a put, you have to pay the cost of the backup. It doesn't sort of drop it off here and say, hey, can you look after that for me? Well, it has to be sequenced. It has to do that. Because if you just sort of asynchronously drop it off, the machine may go away, but you had a contract to safely do something with the data, so it goes across here. In the case of C, it says, well, this partition says, well, it doesn't belong here. It's down here, sends it over, it backs it up, and then it returns. So as far as an API goes, it's just math. You're just doing get and put. But it's resiliently managing your data. Okay? Again, known access, known update latency. Worst case, 2 network hops. Okay? So, what happens if something dies? What happens if this JVM dies? It's somehow told it dead. Lots of reasons why things die. Things die. It may just become partially unavailable, but for long enough, the consumer's dead. It's the difference between whether you're sick, really sick and can't go to work, and you get better, or you're actually broke. So, on this side, what does it mean to die? Well, it's no longer available. Consensus management protocol between these little guys say that, look, it can't be trusted anymore. I don't know what's happened to it, but it's no longer a member of the cluster. It's that team member that just doesn't show up. It's not pulling their load. It's not responding. Having too many failures. We're all trying to send traffic to it, it's just failing too often. It's like, no, it's unreliable. It's gone. And coherence can decide within a second and even less that something has got a processing done. In which case, they all go into action and they all work together. Remember I said, it's a cluster that everyone works together. We don't stop the world and vote. When you vote, when the elections come up, what happens? We all vote and then we all stop and watch the television. No work gets done. In this, they don't vote to see who takes on the next piece of work. It says, right, I'm JVM3, I was the backup B, I'm now the primary B. And at the same time, JVM4 says, well, I'm the primary of D, and I've lost my backup. I'm going to make a new one. Now, the backup for D could have gone over here. We always promote the backups to become primaries, but this backup could have gone over here. Now, at that point in time, this app here is doing a lot of gets on the data. Logically, it can see what's called a single system image. It can see all of the data. It just doesn't have it all. But if I said, this application, even once it's failing, it says how much data is there? It's got 4 elements. Even while JVM is failing, it's 4. And I can get A. If I can get B, then this actually has priority. Recovery is a higher priority than we get. So we do great performance to ensure we have scalability, availability, and reliability. Actually, we have a philosophy that has both ways. So this will wait until it's got a backup, then it will return B. Same thing with D. But if I try and get C here, it'll say, yep, you can see it's got it, it's safe. It's safe for the cluster. The cool thing is, if I add this node back again, it says, hey, I'm back. It says, no, you're not, you're someone new. In which case, it will gradually migrate data back. And you can choose how much data gets migrated at any point in time. Because when a node joins, you know, massive bursts of traffic, and all the apps will go, ooh, I'm a bit slower now, and then it's right now. And so there is no real difference between a member failing and scaling out. It's the same algorithm. All we're doing is moving the partitions around. The only difference with failure is we have to do a bit more work to test if a member is failed. Okay.
Can I ask you a question about that? This is something I might be a naive question, but if that one fails and the other JVMs have got all the memory max set and you can't kind of like distribute it across the others, what happens then?
Yeah, you run a memory.
So the whole thing is going to go there.
It's like I'm running RAID and I've maxed out disk and I pull one out. So you have to have a core. It's the same with people. My boss is sending enough work for John and I. If one of us gets sick, we're maxed out, the other one's going to fail. Yeah. So you've got to have enough. You've got to have enough JVMs. How hard is it to create another JVM? All you need is enough resource for up and run.
In your diagram, when you get it from JVM1, you get C.
Yeah.
Instead of getting it from the, because there's a copy in the background.
Yeah.
Why doesn't it just get a copy from the background?
What happens? Think about this. Down here, I've got another application that I'm doing a put to C. So at the same time, I'm doing a put to here, but I haven't yet got the backup here. So this will be a dirty read. There's a chance you'll get a dirty read. So the gets always go by the primary.
Presumably you have topologies where it work differently.
Yes, there are different topologies. And there's a new feature where you can say, it's not in 3.3 yet, but you can actually say, I'm happy with dirty reads from backups. In which case, yeah, people do that. But that's your choice. From now, we say, look, there's no way we're going to let our customers get dirty reads of data. No way. They're trading all this stuff. They're making decisions in the business. It's like saying to the database, well, give me whatever rating you want. Whatever, I'm going to select whatever you feel like, whatever the latest or recent versions you've got in your cache, etc. So, but we do have customers that say, well, we don't actually do that much updates, so it's always safe to read from backup. And so you have a reduction in network costs. But there are solutions as well to this to problems as well. Okay, so you can do things like tell nodes here that not to store any data. If you've got nodes coming and going from the cluster a lot, they disturb the membership. And you want to say, sure, you can store data, but there's a certain group that are going to store the data. Because group partitioning costs, costs if the moves up across the network, across process network. And there are a whole heap of other things you can do. You can have listeners. Your application can have like swing-like listeners saying, hey, I want to listen for changes in A, I want to listen for changes in C. In fact, I want to listen for changes in everything. I want to listen for changes in a certain subset, in which case the filters get applied where the data lives. You can also do things like, well, compose topologies together and say, well, I don't want to have to go across the Y all the time to get C because I know it's down here. So what I want to do is keep a local copy of it. So we have near cache, which is a combination of the front cache, the local one here, and a back cache partition. So when I go to get B, I can check my local cache. It's not there. I can go and get it from the primary, bring it back, keep myself a copy. And coherence will guarantee that it will keep it up to date for you. So if you suddenly change C down here, this one will get it validated. You don't have to configure anything, you just near cache. So this is the near cache that knows what to do. You can also choose that you want this to be like timed out, or a whole different variety of ways to explain data. You can do queries. So you've got all this data in memory, but it's spread out. Instead of going, well, now I want to find all the trades, you don't go to each machine yourself as an application developer and say, okay, you give me this. You can say to coherence, I'll run a query, it pushes the query to all the nodes, they're executed in parallel locally, and then it aggregates the results and gives it to you. Out of the box. It's like a bit like a database, you can index them as well. You can index any part of your objects. So you can create an index on a project. So I want to index all the trader IDs. So I want to find all of the trades for a particular trader, I can do that. And there's a bunch of these sorts of things. This one's the most interesting for me, for our demo, is that I actually want to do some work. I have a node here, let's call this node B, which has my market. And there's all the current open positions. When I want to place a trade from my application over here, I'm going to say place the trade. I want to execute it here as the market. Because the market could be a big piece of data. And if I have to keep moving the market around to all the different people who want to add data to it, then it's going to be slow, it's going to be inefficient. So I want to keep the data pinned to one place. I want to keep the data in some JVM and then say to it, wherever you are, and I always know where it is because I know it's key, execute this work against it. The nice thing about that is, if this fails, then let's say, well, if this node fails, B is going to be promoted into here. Any work that was occurring against there is automatically redirected, so you don't have to do anything, and it carries on. So during failure, it just continues to work.
You said earlier, so just kind of looking slightly, you said earlier on about basically you were kind of questioning whether databases were inherently sufficiently scalable. And you suggested then that actually to get real proper scalability, you pretty much, or you should pretty much do away with the database altogether. Is that what you're saying, or are you saying that?
How do you scale a database? Well, you get more kit, just more kit. More kit is one way, and that's the traditional way. You can now use things like Oracle Graph and MySQL have got good clustering where they're all active. But they're only active for one. So if I'm doing 1 billion trades a day, you're bound by disk. So the next thing you want to do is, and it happens on small systems, you split it up, you partition it out. So I'm at A to D there, E to F here, and so you write code where DBA starts to partition the data for it. And they statically petition the data and possibly, you've got an API which says this is going to talk to anything. As soon as you do that, cross-database transactions become an issue. And you have to do two phases, at least 2 phases across them, which means you have to block more from the blocking. It doesn't happen in these types of systems. Because coherence is managing petition for you. And typically what you have to do is, if you want to scale out such a database, you have to stop it. You actually have to stop it, reconfigure the cluster, rebalance the tables, and then start it back up again. I'm talking about a system here where I just started the JVM. But behind this, databases are crucial, because we're dealing with stuff in memory. Unless you've got resilient infrastructure, it's sort of like keeping all the knowledge in one Java app and then just turn it off. All the OS just starves of the process, and all the OS actually got a bug in it, kills it, the JVM's got a bug in it. So you need to be able to write stuff to disk. So you can both write and read from disk. So coherence has this thing called cache loaders, and there's a thing called cache stores. So when I put my data into my node here, it writes it to disk first, and then it gives it back up. And then if I get it, I'm just getting hidden cache. So I write directly through my cache into the database. And this is, in coherence, it's just a plugin. It's like an interface with 5 methods on it. You just write one of those configure it probably. And so if I want to load stuff, I can say, well, is my cache here? No. Is it my cache here? No. Like, here's my cache loader, bring it in. Now I'll cache it, I'll make it back up.